Welcome to Learning Unit 11, which is about non-ferrous alloys. In this learning unit, precipitation hardening will be a very important concept, so we're going to review it. Here we see copper-rich precipitates forming in an aluminum solid solution. These precipitates are responsible for hardening material so that it is strengthened, resulting in weight savings when it is applied, for instance, to the construction of fuselages. Precipitation strengthening is a type of dispersion strengthening, and let's review the rules for such type of strengthening. Number one, the matrix should be soft and the disperse phase should be hard and discontinuous. We don't want the matrix to be the hard material, as then a crack can propagate through it, and this results in a material that is brittle. Hard precipitates result in strengthening, and we can see here an example of how a crack is prevented from propagating because of a ductile matrix. Secondly, we want the disperse phase to be small in size and large in number. This is the optimum distribution for prevention of slip or impeding slip. Thirdly, we want the disperse phase to not be of a sharp morphology, otherwise it will act as a stress concentrator. We prefer the disperse phase to be, the precipitates to be rounded in some way. Fourthly, we want the disperse phase should be coherent with the matrix. On the right, we see a coherent precipitate. The reason for this is that a coherent precipitate introduces disturbances in the crystal lattice over a much larger area than the size of the precipitate. This is not true with an incoherent precipitate shown on the left. When precipitates get very large, they become incoherent and less effective at strengthening. Let's see how this is applied to produce age-hardenable alloys, which are common in non-ferrous alloys. Let's look at the example of aluminum-copper alloys that we discussed earlier. The way they are manufactured is that, for instance, we would produce an alloy with a nominal composition of 4% copper. We see that at room temperature it will be in a phase field that is multi-phase. We take the material as produced and we solution heat treat it. This means increasing its temperature until it is a single phase solid solution. This is shown here in step 1. In step 1 we see the material is in the alpha phase. When the material has been thus heat treated and exists in a single phase state, it is then quenched rapidly. When this is done, the single phase situation is retained, but it is unstable, thermodynamically unstable. Through heat treatment, a process called aging, the precipitates, the second phase, which is thermodynamically favorable under equilibrium conditions, begins to precipitate. These precipitates are very finely distributed because the precipitation is occurring in the solid state at a low temperature. This means that diffusion kinetics are slow, and large grains or large precipitates will take a long time to develop. Here we see how the yield strength develops with aging time for different aging temperatures. At high temperatures, we see the aging occurs pretty rapidly. Here we see in just a few minutes at 260 degrees centigrade. We see, however, that with prolonged aging, the properties of the strength of the material actually diminishes beyond a peak value. When the material has been aged beyond its peak strength, it is said to be in an over-aged condition. By lowering the temperature, the time taken to reach an over-aged condition is increased. These annotations tell us the morphology of the precipitates. Initially, we get what are called GP1. This stands for Guinier-Preston zones of type 1. These are almost just an atom layer thick, or a unit cell thick layer of precipitate is forming at this stage. And Guinier-Preston zones too are only a few unit cells thick. After that, we get the precursor of the theta phase. Once the theta phase forms, it becomes incoherent with the matrix, and the effectiveness of the precipitate in causing strengthening reduces, and the material is in an overaged state. If we now wish to get heat treat the material to optimum strength, we must solution heat treat it once again, bringing it back to stage 1 here, quench it, and then age it to for an appropriate amount. The precipitates that form can have different morphologies depending upon the interfacial energy between the precipitate and the matrix material. If the interfacial energy is low, then we get wetting. We see here how the precipitate phase almost seems to flow around the grains in the matrix. This results in a continuous precipitate, which is not favorable for the strength of the material, or rather, should I say, the toughness of the material, because a crack can now propagate through the continuous precipitate. At intermediate surface energies, we see that the angle, what's known as the dihedral angle, is increases, but is not as high as 180 here. And we get precipitates with sharp points. Again, this can lead to stress concentrations. With a high interfacial energy, the precipitate wants to minimize the surface area, or we should really say the Gibbs free energy calculations predict that the surface area to volume ratio of the precipitate must be minimized. This is achieved by a spherical shape. So this type of precipitate would be ideal in terms of avoiding stress concentrations. Here we see an example of a nickel-based superalloy. The precipitate has wetted the grains of the matrix and has produced a continuous precipitate. This is not good for the toughness of the material. Here we see precipitates in aluminum copper, age-hardened alloy. We can see here the precipitates are very finely distributed. They are aligned with the planes within each grain. We talked about the alignment of precipitates with grains, and here we see this is a meteorite, an iron-nickel meteorite, and the precipitation of the second phase in alignment with the grain structure of the matrix material results in this basket weave pattern. This is known as a Wiedemann-Stutton structure. it is very apparent. It is usually not as apparent as this in synthetic materials. In this meteorite, this iron nickel meteorite, it is estimated that in order to produce a Wiedmann-Statten structure that is this coarse and so visible to the naked eye, it would have had to cool at a rate of less than a degree, a drop in temperature over 1,000,000 years. So it is then suggested that these must have formed at the center of an object such as a planet. We talked about Guinea-Preston zones before. Coming back to this graph, I have combined it with some illustrations of Guinea-Preston zones and precipitate. Here we see what a GP1 zone looks like. It is almost an atom layer thick of precipitate, and the thickness of it is about a unit cell. That's called a GP1. So these are embryonic precipitates. GP2 zones are just a few unit cells thick. And then we get the precipitate forming, and when it does so, it is incoherent with the matrix. Here we see that in the GP1 zone that the precipitate is coherent with the matrix crystal. So we expect strengthening from this coherent precipitate to be much more effective than from the incoherent theta precipitate, which forms during overaging. The non-ferrous alloys that we're going to look at today, or in this learning unit, concern aluminum, magnesium, titanium, nickel, copper, zinc, and refractory metals such as molybdenum and tungsten, and noble metals, here gold and platinum. Let's have a look at aluminum alloys first. In this picture, we see aluminum alloys grouped by the main alloying constituent. They are also grouped according to whether they are heat treatable or not. Alloys tend to not be heat treatable in the sense that they cannot be aged when the precipitate formed is not coherent and thus not effective for increasing the strength of the material during aging. Heat treatable alloys may be age hardened. So here we see the unalloyed aluminum. This is given the designation is starting with a number 1. And unalloyed aluminum is an excellent electrical conductor, and so it is used for electrical conductors, and also has excellent chemical resistance. However, it's soft and not very, or can be strengthened by alloying. Here we see manganese alloys of the series, the 3000 series. 5000 series alloys are magnesium aluminum alloys, or aluminum magnesium alloys. Here we see silicon, aluminum silicon alloys are commonly used for castings. Here on the heat treatable side, we have aluminum copper alloys that we discussed before. These are the 2000 series alloys. Aluminum magnesium silicide, we have 6000 series alloys. Aluminum zinc, 7000 series alloys. And there are other alloys that are not shown on this. So the 3000 series alloys, the aluminum manganese alloys, are very are valued for their formability and corrosion resistance. Because of their formability, they are used to form the walls of aluminum cans through deep drawing. So the walls of the can, or the bottom of the can, starts off as a disc of aluminum, which is then drawn into the can shape. However, the aluminum manganese alloy is not hard enough to be used for the can top, to allow it to be opened through the mechanism of tearing a tab. The 5000 series alloys provide a higher strength than the aluminum manganese alloys, but they are not age hardenable. Should be a not there, sorry. Because the precipitates are incoherent with the matrix. Aluminum magnesium alloys are used for the beverage can tops. And this leads to a recycling issue with aluminum, in that we have a mixture of alloys in the aluminum can, and we cannot simply just melt it down and make other cans out of it, because we have a mixture of the ideal alloying constituents. Talked about the 4000 series alloys, the aluminum silicon magnesium alloys, which may be age hardened. The 2000 series alloys, the aluminum copper alloys, are commonly used for structural applications in aircraft. Again, the 7000 series alloys, aluminum zinc, are also used in modern aircraft. And aluminum lithium alloys are particularly high performance, but they're very expensive and only used in demanding aerospace applications. Here we see a typical wing for a commercial jet, and we can see where different types of materials are used. So we see here A for the slats, we see a 2000 series alloy, aluminum copper, nose skins, aluminum copper again, the top panel, aluminum zinc, the bottom panel is aluminum copper, and we have aluminum zinc and aluminum copper. One thing that's not stated here is that for surfaces that are exposed to the elements, they must be coated with a pure aluminum layer to prevent corrosion. We will learn later on that the precipitates within the aluminum increase the chances of corrosion in a material due to the differences in composition. And so these materials must be protected against the elements by a layer of pure aluminum that is bonded on top of them, if they are going to be exposed to the elements. We talked about heat treating of materials, and when aluminum is supplied, it may already be tempered, and so it may have a temper designation as well as a designation indicates the composition. So here are some common temper designations: F as fabricated, O annealed. This is the softest temper, so you may want to use O material if you're going to be doing some forming operations. Here are some temper designations. For instance, T4 is solution heat treated and naturally aged, and not cold worked after that. Cold worked alloys have some numbers after the first two, or the T and the first digit, that indicates the amount of cold working. An example here is the new Ford F-150 has an aluminum body that is stamped from a 6000 series alloy. So we can see what that is, what the composition of that is from here. So it's an aluminum silicide alloy. which has been which has been tempered to T4. So it's been solution heat treated and then naturally aged. So simply the matter of allowing it to cool from the solution heating temperature has allowed the precipitates to form, and it's not supplied in a cold work condition. It is, of course, will undergo cold work when it's stamped. So far we've discussed what are known as wrought alloys. Wrought alloys are alloys that are formed into bars and sheets that will then go on to machining and processing or forming operations. Casting alloys are intended to be cast. Aluminum silicon alloys are attractive because of the eutectic reaction that occurs in the aluminum silicon system. This results in a reduction in the melting temperature, and a more fluid melt that is very good at picking up the details of a mold. Other materials may be added, such as boron and titanium, to refine the grain, and which results in grain size strengthening. And sodium or strontium are added to prevent the aluminum silicon phase from forming needle-like precipitates, and instead form rounded precipitates, and this reduces stress concentrations. And then copper, magnesium or zinc may be added to permit age hardening of the alloy. Here we see the phase diagram of aluminum silicon showing the eutectic reaction that occurs at 12.2% silicon. So this would be known as the eutectic alloy. Compositions around the eutectic point are commonly used for die casting. Die casting involves injecting aluminum melt or aluminum silicon melt into a permanent mold. Here we can see an example of a die cast component which looks like it's some kind of transmission casing. You can see the details that are picked up by the melt in the die cast mold. Magnesium has a higher strength to weight ratio than aluminum, and this permits lighter components to be created of equivalent strength. However, there are a number of challenges to using magnesium. One of them is that magnesium is reactive and has poor corrosion resistance. Another thing is that the melt and the metal is flammable, and certainly the melt requires special handling techniques. However, despite this, we do find aluminum being used in mass-produced products. Magnesium being used in mass-produced products. Quite commonly, things such as camera bodies. And here we see a magnesium jacketed BMW engine. Inside we have it's called jacketed because it's the outside is aluminum, and in the inner core we have just the outside is magnesium, and inside we have aluminum and aluminum core for strength and corrosion resistance. Beryllium is lighter than aluminum but stiffer than steel, and this combination makes it useful for aerospace instrumentation. Beryllium is transparent to X-rays and is also used as windows for X-ray sensors. However, beryllium is expensive and toxic, so it requires special handling during processing. Here we see beryllium mirrors being prepared for the James Webb Space Telescope. Copper is a common material. It is used because it's an excellent conductor of electricity and heat. It's highly malleable, resistant to corrosion, non-toxic, and is easily joined. So the pure material is used quite commonly, particularly for use as electrical conductors. But however, its copper is quite soft, and so alloying is used to increase the strength. Copper zinc alloys are known as brass, and we can see that there's quite a large phase field where we have a single phase solid solution up to 38.9 or should we say 39% zinc. Higher than that, so up to 39% zinc, those are called alpha alloys, to indicate that the material is in a single phase solid solution. Beyond 39%, we get what are known as alpha beta alloys, which contain both alpha and beta. So here we can see some microstructures of an alpha brass. Alpha brass is, you can see the grains here. These are, in fact, it's a solid solution, so it's single phase. And you may see some bands here. This is due to twinning. It's the contrast is not due to differences in the composition. And alpha brass, because it has pretty good corrosion resistance, is used for things such as water connectors in plumbing. Alpha beta brass is stronger, and here you can see the alpha and beta regions in the material, so it's polyphase. And alpha beta brass is good for forgings. So this is where the material is formed while it's hot. Bronze is name given to copper tin alloys, which are stronger than brass. So here we see the phase diagram for bronze. We see that we have quite limited solubility of zinc in copper, up to about at high temperatures you got 10% there, which could conceivably be quenched. But what happens here, we have a eutectoid reaction, which results in the formation of a delta secondary phase. So we can see that in low tin bronze, it's single phase in the alpha phase. And if we go beyond the solubility point, beyond right here, 11%, then we end up with a polyphase material where we get a hard dispersed delta phase. So the material containing delta phase will be harder and will be stronger and have better wear resistance. Other types of bronzes are leaded bronzes. These contain lead and they're used for bearings. There's aluminum bronzes. These are resistant to seawater and biofouling, and they are used, say, to cast ship propellers, amongst other things. And manganese bronzes, which operate under high loads and speeds. Here we see the copper beryllium alloys, which contain between 0.5 to 3 weight% beryllium. And once again, we see here a eutectoid reaction. So with a 3% beryllium, which will roughly be about here, at high temperatures we have a single phase material. But upon cooling it, if we cool it rapidly, we will have a supersaturated solution, just as we saw with aluminum alloys. So with aluminum alloys, we would solution heat treat and then quench. The quench material can then be age hardened to bring out the gamma phase. And that's indeed what is typically done with copper beryllium alloys. Copper beryllium alloys are strong and springy, and they are commonly used for electrical contacts. So here we see a range of electrical contacts that have been stamped and formed out of copper beryllium alloys. Next class of materials we want to look at are nickel and cobalt. Cobalt is resistant to corrosion by body fluids and is used in prosthetics. An interesting alloy is Monel, which is an alloy of copper and nickel that has excellent corrosion resistance. Iron-nickel alloys, one of which is called Invar, are very useful for the low thermal expansion coefficients, and they're used quite extensively now in aircraft production as molds, permanent molds for composite parts. You see, the composite parts have to be baked, and they use Invar because it doesn't expand very much, and hence assures the tolerance, the precision of the molded part. And then there's superalloys, which contain nickel, aluminum and titanium, and they have service temperatures up to 1000 degrees centigrade, and applications of this include the interior of jet engines for the blades. I found out an interesting fact about Monel, which is that it's actually used as a wrapping for steel guitar strings, and some players actually believe it, actually prefer it, and many players do in fact, and it's can be quite commonly found as an alternative string type. Steve Harris of Iron Maiden has been known to have preferred Monel strings for his bass guitar, so I thought I'd throw in some metallurgy of heavy metal music. Next thing we're going to look at is titanium or titanium. Titanium has excellent corrosion resistance. It can withstand high temperatures. It has a high strength to weight ratio and is biocompatible. So if we have a look at the phase diagram, we see at high temperatures, okay, this is I've shown this at high against pressure here, but atmospheric pressure is about 1/10 of a gigapascal, so we're somewhere down here basically. And what we need to worry about here is that at high temperatures, the beta phase, the body-centered cubic phase of titanium, is stable, and at low temperatures, the alpha phase is the hexagonal close-packed phase is stable. So the alloys are named after which phase is predominant at the room temperature. The addition of aluminum and tin stabilize the or strengthen the alpha phase, the low temperature allotrope of titanium. Titanium beta alloys are such where the beta phase is stabilized down to room temperature by the addition of molybdenum and vanadium. And such material can be actually age hardened to precipitate the alpha phase. Alpha beta alloys are very commonly found and sometimes called the workhorse of the aviation industry. So here we have a mixture of alpha and beta phases. And titanium alloys are commonly used for medical applications because they are biocompatible. So here we have an illustration of a knee replacement, I've forgotten the word for it now, an implant for, well, it looks like the root for a tooth implant, And this is an artificial hip joint with a titanium stem. These are polymer bearing here, and then we have I believe this is a titanium insert, but this is certainly titanium. The last thing we're going to consider briefly consider are refractory and precious metals. Refractory metals have very high melting points and are suitable for a high surface temperature. So these materials are such as tungsten, molybdenum, and tantalum, and niobium. Precious metals such as gold, silver, palladium, and platinum are useful in engineering applications as they resist corrosion and are good conductors of electricity. So silicon chips use gold wires because they can be bonded very easily using diffusion bonding to the silicon chip. And so that's it for non-ferrous materials. I hope you enjoyed it. Thank you very much.